Hello, today is Tuesday, October 6th, and I wanted to make another video to talk about number 3 on the non-merit worksheet. I normally don't make videos about the non-merit worksheet because those have full solutions that go up at the end of the day, but I did think there was kind of an interesting twist to this problem that we haven't seen before, so I thought it would be good to talk about in more detail. So number 3 says to consider a surface S, which is given by z squared equals x squared plus y squared. And either I remember from when we studied quadric surfaces that this is the equation of a double cone, or if I don't remember that, I can still kind of puzzle it out by setting x, y, and z equal to constants and seeing what happens. That if x is a constant, then I get either crossing lines or hyperbola in y and z, or if z is a constant, I get circles in x and y. So either way, I should get a double cone for S. And then in part B, we want to use Lagrange multipliers to find the minimum distance, the points on the cone that are the minimum distance away from the point 420. So I'm going to set up, I need a constraint and then I need a function to minimize. And the constraint should be given by the fact that I'm on the surface S. So I'm going to rewrite this as g of xyz should be equal to x squared plus y squared minus z squared equals to 0, just by subtracting z squared from both sides. And that exactly describes my double cone, the surface that I have to be on. And then I also want to know what's the distance from point xyz to the point 420. As usual, I'm going to go ahead and get rid of the square root because what's under the square root is at a minimum exactly when the square root is at a minimum, and vice versa, that the square root will be at a minimum if what's inside is at a minimum. So I'm going to set f of xyz equal to x minus 4 squared plus y minus 2 squared plus z minus 0 squared. And I'm just going to simplify that last one to just z squared. Okay, so f is the function that I'm trying to minimize given the constraint g. By Lagrange multiplier method, I can set the gradient of f is equal to lambda times the gradient of g. The gradient of f should be given by, if I treat x minus 4, what's inside is the inside function, then its inner derivative is 1, and then I can just bring that 2 down, multiply, subtract 1. So I'm going to get, whether I expand it out or whether I use sort of the chain rule, I will get 2x minus 8 for my partial with respect to x. I will get 2y minus 4 for my partial with respect to y, and I will get 2z for my partial with respect to g. The gradient of g is just equal to 2x comma 2y comma minus 2z. So I'm setting 2x minus 8, 2y minus 4, 2z is equal to lambda times 2x, 2y minus 2z. Multiply out to get some new equations in lambda. So that 2x minus 8 is equal to lambda times 2x. 2y minus 4 is equal to lambda times 2y. And 2z is equal to lambda times negative 2z. Now, in a normal Lagrange problem or in a more typical problem, I would expect to have to start dividing things and moving over to try and solve for lambda. But in this case, something happened that doesn't usually with these kinds of problems, which is that one of these equations is already pretty nice to deal with. That if I divide this by lambda, instead of getting something awful with fractions of y, some function of y over another function of y, if I divide this, I would get lambda is equal to 2z divided by negative 2z, which is equal to negative 1. That's totally fine. That's one possibility. Technically, there's another possibility. This statement that 2z is equal to lambda times negative 2z is true if lambda equals negative 1, It's also true if z is equal to 0, though. Now, technically, anytime I do the Lagrange multiplier method, I have to be a little bit careful that I'm not dismissing the possibility of dividing by 0. Although in a lot of cases, that'll turn out to be, it's just not possible. So I think that's true here as well. Let's see what happens if I try setting z equal to 0. If z equals 0, then since x squared plus y squared equals z squared, that should be equal to 0. And we know that only happens if x and y are both equal to 0, because when they square, they're at least 0 or they're positive. So that goes to x equals y equals 0. So if we have z is equal to 0, then x and y should both be equal to 0. But then that's going to be a problem for me because I know that 2x minus 8 should be lambda times 2x. And if I plug in x equals 0 there, I'm going to get negative 8 is equal to 0. That's a problem. Can't do that. So it turns out that by setting z equals to 0, I ended up getting a problem by taking x. I solved to show that that would have to mean that x and y are equal to 0, and that would be a problem. So I'm going to return up here and say that this gives no solution. And that's usually what I'm doing. Anytime that I do the Lagrange multiplier method, I divide out and I ignore the fact that it could have been 0. I'm basically saying, I don't think that one's going to give me a solution. The other possibility is that I use the Lagrange multiplier method, I solve, and I still get something that looks weird. Well, then maybe I need to go back and check, should I have tried one of them equal to 0? In this case, that's going to give me no solution. So it has to be the case, the only possibility is that lambda is equal to -1. So now instead of solving for lambda over here, I'm going to plug in the fact that lambda is equal to -1 and use that to solve for x and y. So 2x minus 8 should be equal to -1 times 2x. So -2x. I'll add 2x to both sides. I'll add 8 to both sides, and I'll get x should be equal to 2. I'll plug in that lambda is equal to -1 here to get 2y minus 4 equals -1 times 2y. So -2y. Add 2y to both sides, add 4 to both sides to get 4y equals 4 and y equals 1. So what I'm saying is that the minimum distance of this function, the distance between 4, 2, 0, given this constraint, will have x equals 2, y equals 1, and now I want to plug back into the constraint to solve for z. So I know x squared plus y squared minus z squared equals 0, or x squared plus y squared equals z squared. And it follows that 2 squared plus 1 squared, which is 4 plus 1 is 5, equals z squared. And thus that z is plus or minus √5. So I'm going to scroll back up a little, and I'll say that that gives me 2 possible points that are actually going to be equidistant from 4, 2, 0, because the distance between 0 and positive square root 5 is the same as the distance between 0 and negative square root 5. So the 2 points that are on S that are closest to the point 4, 2, 0 are 2, 1, square root 5 and 2, 1, negative square root 5. And if this looks at all familiar to you, we did actually have a merit problem, I think last week, where we solved not using the Lagrange multiplier method. Both of them gave us the same answer though. And so for a problem like this, you could go either way. Personally, I think Lagrange is easier. A lot of the time, I actually think Lagrange is easier. But the other method of solving it is still totally valid. So compare this with the worksheet from last week. And as usual, if you have any questions, feel free to let me know.